Okay, so for an example, let's think about the sun and one of the small planets like Mercury or Venus or Earth. So here's the sun, the spherical mass. That's a very bad sphere. And quite a ways away from it is this tiny little planet. The mass of this planet is so tiny compared to this star that it doesn't matter. So in describing the physics of this, you can ignore, in the entire universe, you can effectively ignore this. This isn't a source. The main source is this star. But when you're considering large distances like this, the distance between the planets is way, way larger than the radius or the diameter of the sun. So in models, you can effectively pretend here that there's a mass that's this is being weird, at a singular point that's, in our case, spherical, which displays spherical symmetry. So you can effectively describe the physics of this as a singular mass at a point in space-time, warping space and time. And we want to consider the space-time geometry outside of that point and the matter distribution. Well, as we've said, there's nothing, effectively nothing. We're ignoring all the planets and stuff. We're just considering purely of that point source mass. So outside of that point, our stress energy tensor is going to be 0. So that's our first simplifying solution condition. We're just going to say that our stress energy tensor is 0 for this hypothetical outside of the spherical point mass. Well, let's contract indices. I think that's the jargon used. This is a much simpler equation now. And sum over all UV. That's just going to be 4 in our case. And that's, by definition, when you sum over all UV, that's just R. So R, that can be absorbed together, just some constant times R is equal to 0. Well, that means that R, scalar curvature, must be equal to 0 in this situation. And that removes this whole term, which means for our case, the Ricci curvature tensor outside of this point mass, for the space-time outside of this point mass, beyond this point, is going to be 0. So our plan of attack, as I say, is first we're going to work out the components for spherical symmetry and we're also going to assume that it's static, that there's no time evolution outside of this. It's a point mass and it stays there. It's not rotating. It has no charge. We're going to work out for spherical symmetry what the components of the metric tensor should look like. We're going to plug that metric tensor into the Ricci curvature tensor, set each component to 0, and then we're going to solve each of those, and we're going to make sure that it reduces to the Newtonian theory of gravity in the weak gravity and low velocity limit, and then we'll have our Schwarzschild solution. That's hard to say. All right.
Schwarzschild.
So, yeah, there we go.